Now what we're looking at here is a matrix dot plot small multiple. Now some other names for small multiple view can be a trellis chart. So this is often referred to as a trellis chart. And we're going to walk through uh, what are the mechanics of putting something like this together, what's being represented, and then how do we use it for analysis? Because this is a wonderful, excellent example of utilizing small multiples for analysis. So again, recapping some of the things we discussed before, when we use a small multiple or trellis chart, we're using it for side-by-side comparison. So we have a number of small, similarly encoded views that we put side by side, and that allows us to use our spatial reasoning to compare sort of the spatial layout of the encoding in each one of the views. Now remember some of the rules of making representations this way. We must have shared encoding. So in this example here, we'll see that these are plotted points. So we have plotted points across an x-axis. What we're encoding here and what you see with the blue dots is a measure called yield. And you can think about yield as sort of like output. So if I have an acre of agricultural land or farmland, I plant a particular crop in that farmland, how much of that particular grain, it could be wheat, corn, what have you, do I get out of that acre of land? And so that's a measure, and that's the measure we're looking at here. If you look down at the bottom on the x-axis, you'll see the 20, 30, 40, 50, and 60. So those are bushels, and a bushel is a measurement. You can think of it as a bushel as a big container of barley. And then you'll see it's a ratio per acre. And an acre is a unit of land. Typically, a residential home is built on a quarter of an acre, so you can think about that measurement as sort of the land area that we might build 4 homes on. So hopefully that gives you a sort of a sense of what our measurement is here. And then each one of these views is a particular county that this measurement was taken. So you'll see we have Waseca, Crookston, Morris, University Farm, Duluth, and Grand Rapids. These are each different counties. So if you're familiar with Iowa, likely you might recognize both Duluth and Grand Rapids as counties in Iowa. So these measurements, unique measurements for this barley yield measure were taken in these different counties. And then over on the left-hand side, where we would typically see our y-axis, we see a set of rows. And what these rows represent are different varieties or different genetic strains of barley, so different types of barley, if you will. So when we look at it, Treby, Wisconsin, number 38, number 457, those are each a different type of seed, if you will, or a different strain of this barley that's planted and then grows and is harvested. So sort of the setup here, you can tell that this is a multi-dimensional data set. We've got different county, we've got different varieties of barley, and then you'll also notice in the 2 columns, there's 2 different years. So we see represented here 1931 and 1932, and those are used, 1931 and 1932 are used simply as different categories here instead of a time series. And the difference there, we're not looking at a growth trend from 1931, 32, 33, 34. All we're doing is just making a comparison of the amount of yield or output in one year versus another. So those are our three different variables that you see represented. And then we have our measurement that is the barley yield or the output. Okay, so let's walk through the first example on the left. So one of the unique things about how this example is organized is that the views have been ordered by their median. Now there's lots of different ways to order things. So we could order things by their mean, their median. In this particular case, we have defined it by their median output. So what is that very center measurement? And in this case, we see each of the views. So the way that these counties are stacked from the top to the bottom. So Waseca, why is Waseca on top? Because it has the highest median yield for all the counties. Crookston has a little bit lower median yield. Morris has a little bit lower than that median yield, etc., all the way down. And this would work very similarly if we were using a mean value. We could do the same sort of analysis using a mean. The other thing I want to bring to your attention is that the ordering of the rows on the y-axis is organized by the median output of that particular genetic strain of barley. So, as an example, Trebby has the highest median yield, Wisconsin number 38, the second highest, etc. So each of these is also ordered by the median output of each strain. Okay, and so we've organized this, both the columns and the rows have been organized into the median output pattern. The sort of highest median output, if you would be Waseca for the counties, and the highest median output for a strain would be Trebby. Okay, now let's take a look at each one of these frames. So what I'd ask each of you to do is simply to compare each of the counties. So you can start by looking at Waseca, Crookston, Morris, reading down in the year 1932, and just look at the pattern of these different yield outputs for that particular strain or type of barley. And just get a comparison, just sort of a visual comparison of how these measures might differ from one county to the next. And the first thing we might notice is we can kind of see this pattern of Waseca having the highest median. Most of its dots are further to the right. As we proceed down, maybe let's look at Morris. You see that one's a little bit less to the right. It's sort of in the center. Then we go to University Farms. Most of its plotted points are to the left. Duluth, also to the left, and Grand Rapids clearly to the left, meaning that Grand Rapids would have the lowest yield. And so that you can sort of see this pattern, decrease in median output as we proceed down in the column from Waseca to Grand Rapids, that the median output drops as we move through these counties top to bottom. Now we could also take a look at the same sort of pattern in 1931. So we just move over to the right there, and we kind of look down through the same sort of approach. We see Waseca definitely has the highest median output, and then as we step through Crookston, Morris, University Farm, Duluth, and Grand Rapids, we see the pattern shift to the left. So pretty much the same pattern in both 1931 and 1932. And then we can also take a look at Trebby, sort of the highest median yield, in comparison to its other strains. It tends to be furthest to the right in comparison to its other strains. Now, in some counties, it may be a little bit to the left of one of the other strains, but for the most part, it tends to be furthest right. And as well, we see perhaps some of the lower median yield strains toward the bottom, perhaps number 462 or Savannah Soda are further to the left, and we see that in almost every one of our visual frames. So that kind of gives us a sense of, okay, what are these patterns? What are we looking at here? And what do we see going on? And when we compare these, we focus in on them, we can see a pretty clear pattern when we've arranged these and sorted by the median output. So I'll give you guys a couple minutes just to take a look at these different visual views, small multiple plots on the left-hand side, and just get a sense of the pattern. Okay, so hopefully you've had a little bit of an opportunity to get into the practice of comparing these different similar small visual or small multiple frames, all presented in a side-by-side or on top, on bottom comparison and contrast. And hopefully you can get a sense of how this technique is useful. Now, over on the right-hand side, so many of you guys may have been wondering, okay, that's fine. We've been talking a lot about this one over on the left-hand side, but what about the one on the right-hand side? So the one on the right-hand side is basically organized in reverse alphabetical order. So you'll notice that Waseca's on top. It has the highest alphabetical beginning letter, and then University Farms, and then Morris, Grand Rapids, etc., beginning with the lowest alphabetical letter, Crookston. Okay, so you can see that the views are organized in the columns and sort of reverse alphabetical. Notice that the strains are also presented this way. So we start off with Wisconsin number 38 because W's the highest letter in the alphabet, and then we go to Velvet because V comes before W, etc., all the way to the strains at the bottom that have lower alphabetical letters. Now, take a look at the patterns that we see when we have not organized these or sorted these by median output or by the measure. So I'll give you a couple minutes to take a look at those patterns. So hopefully one of the things you'll notice is that we really can't see much. And I'll particularly bring your attention to notice the difference between Waseca up at the top and Crookston down at the bottom. Okay, see, both of these are fairly similar in terms of yield output. Those two counties are pretty common, but because we've artificially separated them in the view, we've put one all the way at the top and one all the way at the bottom because we sorted them alphabetically instead of by the measure. We don't get a very good comparison here, and we don't really see a pattern that progresses through each of these counties as we move from top to bottom. In fact, it's kind of all over the place. It's high, and then it's in the middle, and then it's in the middle, and then it's on the left, and then it's on the left, and then it's back on the right. And so we're kind of moving all over the place. And the same thing occurs with our strains. So we haven't sorted our strains by the output of the measure, and so they're kind of all over the place too. And so hopefully this gives you a side-by-side comparison of the importance of sorting by a meaningful measure. So we sorted by the median output. We also could have sorted by the mean. Got fairly similar results here. But you can also see if we use the exact same techniques, the exact same data, and we sort it in a poor way alphabetically, we won't see anything, okay? Now, I also want to bring in the concept of layering here. So we discussed that before, where we can, if we have shared encoding, similar type of encoding, we can layer one particular visualization on top of another. And that's what we see here. So Here we've taken our barley yield, small multiple visualizations that we were looking at on the left-hand side of this previous page, and we've essentially layered them on top of each other, and we made one small change. In this view, we had two different columns for the years 1931 and 1932. In this view, instead of using two different columns side by side, we've used color encoding for the measurements of each year. So we see 1931, we've used color encoding of pink. 1932, we used the color encoding of blue. And then we've overlaid these, basically layered them on top of each other. So we took the column on the right, we laid it on top of the column on the left, and so we see both of those sets of measures overlaid on top of each other. And so you see the note that we have here, the year data is now overlaid in the same spatial region. So we're using the exact same x-axis and the y-axis rows sorted by median output. Now, I want you to look at the pattern here. Take a look at all of the pink dotted or plotted points. So start at the top, Waseca, then roll down to Crookston, and then we get to Morris. And notice how those plotted points shift quite a bit at Morris. So they shift quite a bit to the left. Now remember, this has been sorted by median output. And then we go to University Farms, those pink plotted points shift back over to the right. Then we go to Duluth, it eases over to the left, and Grand Rapids eases over to the left. Now what we would expect is that the plotted points in Morris would be further over to the right. So if you start all the way at the top in Waseca, and then look all the way to the bottom in Grand Rapids, and you were to draw a line through the center of all those pink plotted points, you'd notice that Morris, the pink plotted points for Morris, are quite a bit to the left. In fact, they're almost all to the left of what that center line would look like. So that makes us very curious. Let's also take a look at the blue plotted points. So the blue plotted points, are to the left. They seem in each one of these frames, they are to the left of the pink plotted points. So we start with Waseca, then we move to Crookston, and we can see, yep, they're all to the left. And then we get to Morris, and we notice, what's going on here? All the blue plotted points are shifted over to the right. And then we go to University Farms, and we see, for the most part, the blue plotted points are shifted to the left. Same thing with Duluth, and the same thing with Grand Rapids. Now, what's going on here? So we've got this trend line of the pink plotted points that moves from top right to bottom left. We think we have an established rule where the blue plotted points are to the left of the pink plotted points, and that seems pretty consistent. So it seems like we've got these two rules here. But with Morris County, we seem to have some problem there because it doesn't follow the rules. So we've got some strange thing going on there. The pink plotted points don't fall in line with our trend line. The blue plotted points seem to break the rule of being to the left of the pink plotted points. And so what you guys see here, this is an anomaly. Now, in some cases, this might be considered an insight. But in further and deeper analysis, what was found here is actually the data measurements for 1931 and 1932 were actually recorded wrong. The measurements from 1932 were recorded as the measurements for 1931, and vice versa for the 2 years on 31 to 32. So that's what accounts for this anomaly. There was actually human error in recording the data, and that's pretty easy to see when we use this layered example. Now, a little bit of commentary about knowing what we're measuring. So this particular example, or sort of caution, provided from Randall Munroe and it made the rounds in the visualization community and a number of different blogs and websites. And walking through, and again, this is presented as a humorous example. But the first thing is we're taking a look at our site's users. So we look in the top left-hand side and we see sort of a pattern across the geography in the United States. We see where the green areas are, the yellow areas are, and the red areas are. So red is obviously more intense than the yellow, and yellow is more intense than the green. Okay, so that's where our site's users are. Then we move to subscribers of a magazine, Martha Stewart Living. And we look at this and we say, we see the green, we see the yellow, we see the red. Kind of looks like the same pattern. And then we look at consumers of furry pornography, which I have no idea what that is, but we see a similar pattern, green, yellow, and red. The intensity seems to be the same in all three of these charts. And so, of course, the business implications are clear. So coming down to the title of this, which is, of course, labeled Pet Peeve number 208, the geographic profile maps, which are basically just population maps. Okay, so what's being represented in these three different geographic data visualizations, is not necessarily what's going on with our site's users or the subscribers to Martha Stewart Living or consumers of some particular type of internet product. What's really going on is this is where people live. So more people live where the red dots are, fewer people live where the yellow dots are, and even fewer people live where the green dots are, or vice versa. So what this is a caution to make sure you understand what you're measuring. And I'll also present this to you in another alternative. If you guys provided any example to me of, I want to know where the most cars are owned, or I want to know where the most hot dogs are consumed, or I want to know where the most books are read, I can give you the answer to every one of those questions represented by states. The answers to every one of those questions from a state perspective, the top 4 states for consuming all of those products, and quite frankly, every other example you might provide to me, would be New York, California, Texas, and Florida. Now, some of you guys might be surprised at the ability to predict the outcome of the answers to every one of those questions for the top 4 states. But it's really quite simple, and I'll explain it in this way. Those 4 states happen to be the top 4 states for population. Basically, those are the top performing states where people live, okay? And the answers to every one of those questions is highly correlated to population. Where do people live? Okay. So in a couple of different ways, this is the caution on when you're utilizing geographic maps. Truly understand what you're representing there and don't just count things. And so now we'll use a real-world example to understand context in the usage of a geographic map. So starting over on the left-hand side, what we have here is a number of train stations. This happens to be train stations in New York. Some of you guys may notice this as a map of downtown New York City. And these are what's represented on the left-hand side, the map on the left, is the number of crime incidents reported in each train station. And so we'll see smaller circles, larger circles. The smaller circles mean the count of crime incidents was lower, and the larger circles means the count is much higher. Now, if we use this particular map to make decisions. So perhaps we're deciding which train station to live close to. Perhaps we're making this to decide which train stations we will or won't get on or off. We might make some mistakes. For example, if we look at some of the largest circles here, we might say, man, I'm not going to live close to those train stations, and I might decide instead to live next to one of the small dot train stations. Okay. Now we're going to talk about why that might have been a big mistake. So now I move to the visualization frame on the right. And in the visualization frame on the right, this has been represented with a ratio. So now we've taken crime incidents, so the number of crimes. So let's say that we had 10 crimes reported in a train station. And then I divide it by 100,000 riders. So what this does is gives me a new ratio-based measure for each train station, how many crimes were committed per rider or per 100,000 riders. And what this ratio does is it gives you a normalization of the data. It presents the data in context and helps you make a good decision about which is the safest train station. So when we look at the map as presented in a ratio, there's a very different picture. And there's one sort of glaring example. We see the largest dot on the map, sort of in the bottom right hand. And this happens to be at an airport. And if we chose to live close to this particular train station, we might have made that decision looking at the map at the left. It's a very small dot. There doesn't seem to be too many crimes reported. But then we move over to the right-hand side, and we notice that that's a very unsafe station because when we look at the number of riders per 100,000, there's a large number of crimes committed per 100,000 riders versus some of the other train stations. And this is also sort of a reminder of the perils of simply counting anything, making counts per train stations, making counts per state, making counts per county. Those aren't normalized. And what you may be doing is just counting the population of either riders through a train station or the population of folks that live in a particular county or a particular state. So I'm going to encourage all of us to utilize this approach of creating a comparable, use a ratio. And one of the ways that we would do that, particularly in Tableau, is we would create what's called a calculated field. And a calculated field is basically it's a formula. So we might take, for example, in our previous example, the number of riders. So we might take the number of riders overall, that's our denominator, and we divide that into the number of crimes. Or said a different way, we take the number of crimes that occurred in a train station, divide it by the overall number of riders in a time period like a year or a month, and we come up with a ratio or a calculated field for those two measures. So some equivalent context starters. We might have city comparisons. So if I'm doing comparisons in a city, I might take some measures like population, gross domestic product, or area. So I might want to look at population within a square kilometer as an example, or the gross domestic product within a square kilometer. People comparisons. We can look at age, income, their size, physical size, education, and we might be able to draw different ratios based on some of those factors. Business comparisons, customer churn rate. So what percentage of our customers leave compared to the overall number of customers? Again, it's a ratio. What is revenue per customer or net profit per customer? Industry comparisons. Number of skilled workers, perhaps divided by number of participants in that industry. That might be a more effective comparison versus number of skilled workers divided by the population. Country comparisons. Of course, we can compare populations, but we might want to compare density. So population divided by area, or the gross domestic product divided by area, or the gross domestic product divided by population. So basically, how much output is there per person in a particular country? So it's sort of the efficiency of the individual, if you will. So these are all presented as just context starters or ideas on how you might put together different ratios for different types of comparisons. So here we'll see an example that was provided through the Quartz online media website. The author was Richie King, and the data was provided by Glassdoor. And what this does is provides a small multiple comparison. The title is How Long a Typical Worker Will Have to Work to Earn What Her Company's CEO Makes in a Single Hour. And there's a footnote here assuming no holidays or overtime. So we're basically just using the standard calendar, 365 days in a year, and no overtime. So no extra hours, but we're also not including holidays. So they sort of explain to us in detail how they've taken these measurements. And then what we see here is a little bit of a matrix that moves from the left to the right. So McDonald's, so if you are a typical worker at McDonald's, sort of the average worker at McDonald's, how long does it take to earn what the McDonald's CEO makes in an hour? And we see here that the average worker at McDonald's, it would take them 6 months and 4 weeks, so basically half the year, to earn what their CEO earns in an hour. We progress through Starbucks, Dollar General, Gap, TJ Maxx, Target, etc. And we'll look at the example over on the right, AT&T Wireless. So the average worker there, what they earn compared to how much the CEO makes in a single hour. We find here that the average worker at AT&T Wireless, in terms of earning, earns the same amount as an hour of their CEO's pay in a much shorter time period, so 3 months and a week. And this is kind of just a small multiple comparison that gives us some sense of, from one company to another, at least in comparison to the ratio of CEO salary, how the average employee does better or worse using this particular ratio of employees' compensation compared to an hour of the CEO's compensation. And the comparison is, of course, over time. So comparing the number of hours it would take that normal employee, average employee, compared to an hour of the CEO's time. Now, here's a simple bar chart using some of the same data of a comparison between countries. So if you're choosing a country to become a CEO in, which one would you like to choose? So clearly, if looked at in terms of the ratio between CEO and average worker pay, it really pays to be a CEO in the United States, that you can earn 354 times what the average worker and your employee makes in the United States. And we can also see that the United States generously rewards its CEOs compared to other countries. So Switzerland and Germany, that number is basically cut in half. The ratio is cut in half. And the interesting thing in this data visualization that I want to bring to your attention is the usage of the ratio. So we're basically making a comparison of the ratio of CEO pay to average worker pay, and we're just comparing the multiple. And this is yet a third way to look at some of the same data that represents the worker's pay. So you see here the worker on the left-hand side, their unit of annual salary, if you will. So we see here the worker has 1, that's their annual salary. And then on the right-hand side, we compare the CEO's compensation in the same units of worker compensation. So, and what we see here is that average CEO, we see 354 equivalent units compared to the worker. And that might give us, in comparison to the ratio that's presented here, it gives us a little bit better appreciation of what 354 to 1 looks like in terms of comparing the area of these circles, the aggregate area of these circles, as if it were equivalent to the financial compensation. Now, an example of a small multiple bar chart. So we see here, this one provided by the inventor of D3, the creator of D3, Mike Bostock. And what we see grouped together here are some comparisons between states. So we see California, Texas, New York, Florida, Illinois, Pennsylvania across the bottom. And what these different categories are, the different colors of the columns in our chart, are age categories. So on the far left-hand side, in light blue, we see under 5 years, then proceed in purple, 5 to 13, 14 to 17, and then finally getting to the category of 65 and over, presented in orange on the right-hand side. And the reason why it's a small multiple is you'll notice that the spatial positioning of the columns is identical from one state to the next. So I can basically take a look at the whole group of California and compare that to the whole group of Texas, or I can go through and make individual category comparisons because they're represented in the same spatial area. So this is just an alternative example of using small multiples with the bar chart instead of plotted points. So also from Mike Bostock, an example of stacked column charts compared to multiples. So here we move from stacked and then we move to multiples. So basically we've just separated those, but the separation versus the stacked column chart or stacked bar chart provides us the ability to make a little bit better comparisons of the quarterly performance of one group, say for example, group 1 in quarter 108 compared to group 2, 3, and 4, as well as I could compare moving to the right as well. Now, this is a set of small multiples provided by Nathan Yao, and visualize this. And it's presented as an analysis of sequels, basically movies that had multiple installments, basically a trilogy. So there were 3 movies with the same characters that all one led to the next. And the title here is Fresh Originals, Rotten Finale. So what it is sort of an analysis of, was the movie good or not? So if the movie was good, it's considered fresh and encoded with green. If it's rotten, it's red and encoded, or if it's rotten, it's encoded with red. And then from that, we have a number of different movie franchises here that are encoded with their revenue performance in the form of a bar chart, a column chart, and whether it was voted on a particular website called Rotten Tomatoes as being fresh or rotten. So we get a little bit of 2 measures encoded here, the financial performance, but we also get sort of the critical review of whether it was fresh or rotten. So there's 35 different properties here, 35 different trilogies. One of the insights is that 23 of them had fresh originals. So out of this whole set of 35, if we look across and compare the first column in each of them, we'll see that 23 of them had a green column. So basically 23 of these franchises started off with a fresh original. The second insight is only 11 of these franchises ended with a fresh finale or fresh third film. So then we could take a look at what's the third column in each of these. And as we start reviewing through there, we can see, yep, not nearly as many have a green finale. And then we can simply compare each of these, the entire franchise, of one to another to say, well, in some sense, which was the better franchise. So as an example, we might look all the way down at the bottom. We look at Toy Story, started off fresh. Each installment was fresh. 1, 2, and 3 was all fresh. All produced a lot of revenue. And we might compare that, as an example, to Free Willy. So we go up toward the top on the second row there, we see Free Willy, also franchise for kids. It started off rotten, encoded with red. It looks like it stayed rotten all the way through, and it got more revenue in the first installment, a lot less in the second. It got a little bit more revenue in the third, but the critical review is pretty much all rotten. Okay, so we can make some comparisons between the franchises of these trilogies, just with this simple color encoding and with the height of the bars. Another set of small multiples. So where is it safe to live? So this one's also provided by Nathan Yao. So this one is positioned on sort of where is it safe to live, and what it encodes is major crimes that are committed, basically felony crimes. Each of those unique felony crimes is color encoded, so we see robbery, forcible rape, murder, larceny, burglary, aggravated assault. So each of these has a different color encoding. And then we'll see Florence Nightingale's coxcomb diagrams come back into view here. That's the type of data visualization that's represented for each of the states. And so first we start off with the United States as a whole up in the top left-hand corner. And this is probably a pretty smart idea because it gives you a sense of what are the overall crimes in the United States. And it gives us a comparable, sort of a sense of what's the mean, if you will, in the United States. And then we can start looking at different states. So if we move just to the right, we take a look at Alabama. In comparison to the overall United States, it looks like people really like to steal things in Alabama. So we've got high or higher rates of burglary and larceny and theft on average. If we now go to the second row, we might take a look at District of Columbia. So that pretty well stands out. And we find out that it looks like District of Columbia is a pretty dangerous place to live. So the rates of robbery, aggravated assault, murders are fairly high, and we might also get some of our stuff stolen there, at least from a larceny standpoint. Notably, it's better in a couple of other categories. Both the rape and burglary categories are comparably low there compared to the United States average. If we take a look at Florida, just to the right of there, we can see that Florida seems to be higher than average rates of assault. So it looks like you might get hit there. Folks may break into your apartment and steal stuff, or folks may just steal stuff from you. Sort of proceeding further down, we might take a look at Tennessee, perhaps Texas, Oklahoma. Maybe we look over at South Carolina, New Mexico, and some observations that have been made before. If we look at a lot of our southern states, the rates of aggregated assault, burglary, and larceny and theft all seem to be a little bit higher for some of the locations in the South, or some of the states in the South. Now, with that said, it would be fair to say, it would not be fair to say that it's only those states in the South, because we see, for example, Washington has some of this same pattern. We see some similar pattern, at least with burglary in Nevada, and a little bit of that pattern perhaps in Maryland. But hopefully you guys get a sense of how to use a small multiple as a comparison of one place to the other. And of course, the question that we began with, we started out with answering, where is it safe to live? And visually, we can take a look at this overall chart and pretty quickly start to zero in on some particular states that it might be a little bit safer to live. New Jersey stands out, New York stands out, Vermont, Rhode Island, Virginia, perhaps North Dakota. So there's some of these states that have overall pretty small amount of crime. So we're able to make those comparisons pretty quickly from a visual standpoint, just looking at the size of the colored shape comparing one to another. Now, this whole discussion that we've been having on when do I use multiple views, sometimes that's a little bit difficult to figure out. What's the logic behind it, and how do I determine whether I should be using multiple views? So what I've provided for everyone here is a matrix on basically rules on, should you or should you not use multiple view. And it goes through some of the rules. There's a diversity of data. The data is complementary. Do you want to do decomposition, parsimony, space and time resource optimization? Is there some self-evidence, consistency, attention management, etc.? So I'll leave this for you guys to utilize as a reference guide, but it gives you the underlying rules that are appropriate in deciding to use a small multiple. Now, a little bit of commentary on utilizing ClickView to create a small multiple or trellis chart. So we'll walk through sort of the basic process of creating one. So the first thing I might do is create a new ClickView file. So I create my new file, and then I'll select Edit Script, and then I'll choose the menu path, New Sheet Object, Chart, and I'll select a trellis chart. In this particular case, you guys will be creating a trellis chart or a set of small multiples utilizing this measurement of youth employment population. So similar to the small multiple comparison for European countries that we looked at before. Now we'll need to select our particular dimensions here. So on the left-hand side, we'll see our table columns. We might take a look at total employed young adult population. If we want to add particular dimensions, we'll select them on the left, highlight them, click on the Add button, and it will move it over to the Use Dimensions or Selected Dimensions window. We might want to make a few tailoring adjustments. Perhaps we want to suppress when the value in that particular, the values in that particular group are null. That might be useful. As well, because we've selected a trellis chart, we need to make some settings here. So we'll click on enable the trellis chart. We'll define the number of columns. So just like in our Barley comparison, we need to determine how many columns of small views we have, and then how many rows of small views we intend to have. And here we've defined a 2x2. You can certainly change this to be whatever the number is that you're working on. Now notice that we've selected this 2x2, and when we select Create Trellis Chart, it will provide us with a slider up at the top, as well as a list box of the different countries that we might bring into our trellis chart. So in this particular configuration, we have a 2x2, we have a slider on top. Notice that we have the different age categories, and then we can select different countries to look at on a side-by-side basis. Okay, so hopefully that gives you sort of a simple, quick overview of how to create a trellis chart in QlikView. We've had a long discussion on what are small multiples, what are layered, what is multi-view visualization, and so now we will summarize those points. So multi-view visualization solves visualization problems. So there's particular problems that a multi-view visualization can help us solve. Small multiples, which is one of the types of multi-view visualization, gives us many views of the same phenomenon side by side, so we can make comparison and contrast. Small multiples work best with a common measure or a mean. So if you will recall, we sorted our small multiple views by the median measurements. So I would encourage you guys, whenever you're working with small multiples, to take a couple different views of it, do some sorting with the median, the mean, and see how those are displayed, sort of introducing a common mathematical measurement versus a more arbitrary one like alphabetical. Understand the context of your data. So remember that it's important to find some type of ratio, some sort of common comparison between categories. We can get into a lot of trouble if we just start counting, number of cars or number of sandwiches eaten, because what we'll typically end up with is an analysis of what the population is, thinking that we have some other kind of insights, when really what we'll end up with is just a count of the number of people who live there. So understand the context of our data. Make sure that we know what we're measuring. Again, don't just measure population. Create some ratio that gives us a sense of what is the analysis like for a day in the life of an individual that works for a company or that rides through a train station. Visual encoding has to be the same in order to do a small multiple. So if I want to make comparisons of these small views, I have to do all plotted points, or I have to do all bar charts. I have to use the exact same visual encoding, or the small multiple technique will not work. We have different levels of encoding. So I may wish to encode the same sort of bar charts for both the overview or detail, or I may want to have multiform data encoding where the overview is a bar chart, but the detailed is plotted points. Remember that we can also layer. So I can take two equivalent views. So if they use the same x-axis, y-axis, if it's measuring some of the same data, I can often layer that on top of each other and take a look at how the common variable interacts with the unique variable with two different unique variables. And then also remember that we have navigation. So If small multiples isn't the right way, that side-by-side comparison on the same view, we can then go to navigation, perhaps have a navigation multi-frame slideshow, animated data visualization, or a video that helps us solve some of those limitations from screen real estate if we need to focus on the process or difference in behavior of the variable versus a side-by-side comparison. This concludes the lecture on multiform data visualization.